Hello, my physics students. It is Mr. Hartley recording inside of the 5th floor storage room because my room stinks of formaldehyde. If you were wondering what outside of the window looks like in the storage room, it looks like that. Sorry, it's upside down. Hang on. Look at that. Cool. Go Cards. Okay, so it's very stinky in here. It's very stinky in my room because it smells like formaldehyde because Mr. V is dissecting sheep brains. But I wanted to give you some force diagrams notes despite all of the chaos. Okay, so this note sheet is to help you get some practice in drawing free body diagrams as a key skill in the forces unit. So let's jump right in. This example problem is: a friend has given you a truly special 12-kilogram box of chocolates as a reward for your fine work in physics. The box is resting on the smooth, which here means frictionless, horizontal surface of a table, so we won't have to account for friction in this problem. Determine the weight of the box and the normal force acting on the box, and draw a free body diagram. Well, let's draw our free body diagram first and name all the forces that are acting on the object. So let's first draw the ground there, and then our box is resting on top of it. And it might be nice to draw some sketch lines here to show that this is the ground right there. Okay, now let's draw all of the forces. Well, there is a force acting on it downwards. That is, of course, the force of gravity, Fg. And I don't know if I mentioned this in a previous lecture, but Fg, we've got an equation for it. The equation for the force of gravity is just the object's mass times the acceleration of gravity. Okay, so we'll have that over here. We'll calculate it later. And then there is another force acting on this box, and that is called the normal force, F sub n, the normal force. So in this problem, we're asked to calculate the weight of the box and the normal force acting on the box. Okay, so first, let's calculate the weight. We've got an equation here that says the weight, or the force of gravity acting on this box, is its mass times gravity. So let's plug in. We've got 12 kilograms of box here. 12 times the value 9.8, which is the acceleration due to gravity, gives us a value of about 117.72 newtons, which, if we account for significant figures, that's about 120 newtons. Newtons is the unit of force. Okay, well, what is then the normal force acting on the box? Well, we can think about this situation. If the box is just resting on the surface of the table, its velocity is 0, and it's not going to move anytime soon, right? It's just sitting there, so its acceleration must also be 0. So we've determined just from some logic here that the acceleration is equal to 0. Our Newton's second law equation says that if F net equals mass times acceleration, well, we just said that the acceleration is equal to 0, which means that the net force must also be equal to 0. That means that the sum of forces, F net, in this case is equal to the normal force pointing upwards. I'm going to give it a positive value, F normal, minus this force of gravity acting downwards. It's in the negative direction, minus 120. But we just said that F net is equal to 0. So something minus 120 equal to 0. What's the something? Well, that's got to be the normal force is equal to 120 newtons. So this would be down. Gravity force acts down. And the normal force acts upwards. Okay. Simple example. Let's complicate the situation. So, our friend, whoever this person is, pushes down on the box with 30 newtons of force. What is the normal force acting on the box? Draw a free body diagram. Well, here's our box again. And there's the ground. And our friend, quote unquote, is pushing on the box. So now we have an additional force. So, F gravity. And then the force, I'm just going to draw it like over here. You can draw it like that, that's fine. Okay. The force applied by the friend is equal to 30 newtons, and then there's a force upwards. That's the normal force. Okay. Well, we still know that the box isn't like sinking through the table. So assuming the table doesn't break, okay, and the box is not moving, which is a fair assumption, the acceleration is still equal to 0. So assuming the table doesn't break and all that stuff, acceleration is still equal to 0, which means that F net, which equals ma, is also equal to 0, which means that we can write the sum of forces like this. Sum of forces, F net, is the sum of all forces. So I've got two forces acting in the downwards direction and one acting in the upwards direction. So the force normal is going to be positive assigned values, and then I'm going to subtract away the force of gravity, which was 120, which we calculated before, and then also subtract away 30. Okay, and now this is equal to 0, right? So I've got 120 minus 30. This comes up to a negative 150. So I know now that something minus 150, what is that something got to be? The normal force has got to be 150 newtons. Okay, so the normal force increases in response to this person pushing down on the box. That's important. That's important because the normal force is a Newton's third law. Newton's third law. It is part of a reaction-reaction pair. The box is pushing down on the table, and in response, the normal force responds with an equal and opposite action. So it is equal and opposite to the forces pressing down on the table. Okay. So is it accelerating to this force? No! Acceleration is 0. No, it's 0 meters per second squared. No, not accelerating. Okay. If instead you pull up on the box, pull upon the box, pull up on the box with a 30 Newton force, what is the normal force acting on the box? Well, let's draw a free body diagram. Free body diagrams. There's our force of gravity. And now we pull up, maybe we're attempting to lift this thing, with a force of 30 newtons. And then there's also this normal force, which is pushing upwards on it, F normal. If I had a little bit more space, it would be totally appropriate to draw the vector from tip to tail. So I could draw it there. I just don't want to go over the words here. So to keep my diagram neat, I just put it over there. That's fine. Okay, so now we have a new situation. The F net is equal to ma, and that is equal to the normal force pointing in the upwards direction. So I have a positive sign here. It's just implied, right? Plus 30 minus 120. This gravity force stayed the same. Okay? Gravity force is the same. The normal force must change in response. Okay? It is not accelerating. I'm pulling up on it. It's not accelerating. Okay? I'm not able to overcome this massive force pressing down on it. Okay? So now I can calculate what the new normal should be. So I move this stuff over to the other side. So I get 30 minus 120. That leaves me with minus 90. And so I have F normal minus 90 equals 0. And then the normal force, of course, would then be 90 newtons in this case. So it decreases, right? We pull up on the force. The table, in response, feels less of the gravity force, which means it's responding with just the force that it sees on the body itself. So Newton's third law says action and reaction. Okay, so that's just 90 newtons in this case. No, the box is not accelerating. Its acceleration is equal to 0 meters per second squared. Okay, let's take a look at the next part. Now, the friend is going to give up and decide he'll drag the chocolate to our car. Again, maybe trying to give us a little bit of confidence here. Dragging the chocolate to the car. He pulls horizontally with a force of 30 newtons. And remember, we said this is without friction because it said that this is a smooth, frictionless tabletop. So maybe this tabletop is made out of some kind of magical material. Let's call it Hartlium. Okay, so the table is made of Hartlium, and it resists. There is no friction between any surface and Hartlium. Okay, so no friction here. No friction. Now we're dragging. We're dragging. So what does that imply? Well, let's draw a free body diagram. There is the floor. People are like throwing things in the hallway. I'm a little distracted. Okay. There is the floor. We have, again, our two forces. The force of gravity acting downwards and the normal force acting upwards, F normal. And then the person is dragging the chocolate to our car, so I'm just going to draw this as an arrow pointing to the right. This is a force applied. Could have drawn it to the left, doesn't matter. Doesn't specify. It's fine. And now we have a good way of representing this. Hey guys, remember in kinematics when we split up the motion into 2 dimensions? Guess what? We've got 2 dimensions here, don't we? We've got all of the forces acting in the y direction and all of the forces acting in the x direction. So we can split it up the same way. Vectors work the same way. We can just deal with each dimension separately. So this is how I'm going to do it. The sum of forces, also called the net force, can be split up into F net in the y direction only and F net in the x direction only. Well, what is the force, the net force in the y direction? I argue because it's not floating into the air or sinking through the matter of the tabletop, it is still just 0. The net force is 0. Why? Because the acceleration is 0. The acceleration in the y direction is 0. Okay? That implies that the net force is 0. Okay, how about the net force in the x direction? Well, let's think about that. F net x. What are all the forces acting in the x direction? Well, we've just got one. It's just the force applied. It's just the force applied. Force applied. That's it. So it's 30 newtons. Okay. Is the box accelerating now? What is the value of its acceleration? Well, this is actually something we can work with, right? Because we said F net equals ma. So that's equal to the mass of the box times the acceleration. We said this was equal to 30 newtons. So we can rearrange this. Rearranging, we get the acceleration by itself on one side. So I'm going to divide over m. I'll get the equation acceleration equals F net divided by m. And then I'll just plug in. So I have the net force in the x direction only. So this is the acceleration in the x direction. This is the the net force in the x direction only. Okay, I have 30 divided by the mass of 12 kilograms, which if I do that in my head, I get 30 divided by 12. What is that? Okay, that's 2.5. 2.5 meters per second squared. Cool, there's our acceleration. All right, finally, you decide that the box of chocolates is too large to carry, and you decide to drag it across the table. You pull on the box with a force of 30 newtons at an angle of 35 degrees, above the horizontal. What is the normal force acting on the box? What is the acceleration of the box? Draw a free body diagram. Okay, this one we're really going to need to draw a free body diagram, because guess what? This thing has motion in 2 dimensions, or it has forces in two dimensions, rather. We're going to determine whether it has motion in 2 dimensions as well. Okay, so all of our same forces apply. We've got that force of gravity pulling it down, normal force. And now, let's draw that force that's pulling upwards on it at an angle. So, I've got my force applied at an angle. I've got this horizontal. And the angle theta is equal to 35 degrees. And the force applied is equal to 30 newtons. So this vector here, the magnitude of this vector is 30 newtons. Okay, so now we know that we can split the motion up into 2 different dimensions, so let's do that again. I've got that the net force in the y direction, and I can set up the net force in the x direction, right? Well, what are all the forces acting in the y direction? I have the force normal, and then that's a positive because it's going up. Then I got minus the force of gravity. But then I also have this acting in the y direction, don't I? Because it's a diagonal vector. It has components. Yeah, we've got to break this down into components that are acting in both the x and the y direction. So I claim that I can name this vector force applied in the y direction, and then subsequently I would have a vector here that would be the force applied in the x direction. Okay, let's put that into our equation. I'm getting some light shifting around here. It's a cloudy day. Okay, so these clouds are letting the light shine through. So this F applied vector in the y direction is pointing upwards, so I'm going to assign it a positive value. So I've got plus FA in the y direction. Force applied in the y direction only. Okay, and then I've got F net x. Well, what's the only force acting in the x direction? Well,